Hi everyone, let's talk a little general chemistry. So today what I wanted to present was two guidelines on how to predict the number of bonds an element usually makes and how to predict whether a bond is going to be ionic or covalent. And then we have the special coordinate covalent bond, quick little topic we'll go over. And then we'll talk about how to name covalent compounds. Thankfully, it's very similar to naming ionic compounds, which we discussed in an earlier video. And then we'll end this video with a formal presentation on how to do Lewis dot structures. I know we have a quick way of doing it in another video. We kind of went over that pretty quickly, but here's a step-by-step guide on how to make a good Lewis dot structure. Okay, let's see those guidelines real quick. Okay, so how many bonds are we expecting each element to make? Well, the guideline is, and it's just a guideline. It's not a hard and fast law or rule, but it's a guideline. So plenty of exceptions to it, but simply this. Okay, the number of bonds that an atom is usually, there's a lawyer talking, usually, not always, it usually equals the number of electrons the atom wants to gain or lose in order to achieve a noble gas electron configuration. What does that mean? Well, let's just do an example. Let's look at oxygen. Hey, oxygen, what do you want to do? How many bonds do you want to make? Well, it's in the 6th column, so it has 6 valence electrons. And then the noble gases are in the column 8 here. They have 8 valence electrons. So oxygen wants 2 more. Oxygen's chemistry is all about trying to go snag, steal, or borrow 2 more electrons from somebody, or maybe a couple of atoms to get 2 electrons. And if it had those, it would have the same number of electrons as neon. It would have 10 electrons, and its shells, oxygen's shells, would then be filled just like neon shells. And there's something stabilizing about having filled shells. Okay, so oxygen wants 2 electrons. Well, then we would predict oxygen should make 2 bonds. Yeah, simple as that. Let's see, sodium over here. It is in column 1, has 1 valence electron. It's thinking about going up to 8 and says, whoa, there's no way I can get 7 electrons. How about I just dump off this 1 electron? I have 11 electrons. If I lose 1, I'll then have 10, the same as neon. So I'm not looking to gain. Sodium's looking to lose. It wants to lose an electron. So there you go. And so if it loses 1 electron, it'll have the same electron configuration as neon. That's stabilizing. So lose 1 electron means go make 1 bond. Whereas column 2 elements want to lose 2 electrons, so they want 2 bonds. Aluminum comes in with 3 valence electrons. Okay, does it want to pick up 5 more to have 8? No, it's easier to lose 3. So out it goes. So aluminum wants to make 3 bonds. Carbon's in column 4. Okay, do you want to lose 4 or gain 4? Well, 4 is a number. It wants 4 bonds. Whether it's going to lose or gain, we'll get to that when we talk about covalent bonding. But 4, that's it. So just to verify, here I got water. If I draw the Lewis dot structure, we'll do more of those later. Oxygen is making 2 bonds. Yep, and that's what we predicted. It wanted 2 electrons, so it's going to make 2 bonds. Hydrogen is only making 1 bond, right? Only 1 line to hydrogen here, 1 covalent bond. Yeah, because it had 1 electron. It would like 1 more like helium, so it wants 1 more electron. Wants 1 to gain, means it wants to make 1 bond. What about carbon dioxide? Well, we said carbon is in column 4, gain 4 or lose 4, 4 bonds. There's 2 oxygens. Each oxygen wants 2 electrons or wants to make 2 bonds. So it actually is going to form a molecule with 2 double bonds, right? So this oxygen has 2 bonds. That's what we would predict. It wants 2 electrons, makes 2 bonds. Whereas carbon has a pair of double bonds. And altogether there's 1, 2, 3, 4 bonds to carbon. Yeah, that's what we predicted. 4 was the number of electrons to gain or lose. Cool. Magnesium. These are all examples of covalent bonding. But when you have a metal, magnesium with a nonmetal, right? So magnesium's on the left side, metal. Chlorine's on the other side of the staircase. It's a nonmetal. That's going to make an ionic bond. How many bonds? Well, magnesium's in column 2, so it wants to lose 2 electrons and become a +2 cation. Chlorine, however, wants to gain 1 electron. It's in column 7. It wants 8, so it needs 1 more. Wants 1 more electron. It's going to make 1 bond. So each chlorine wants 1 bond, so it's going to make 1 ionic bond if you're focused on the chlorine. Chlorine wants to make 1 bond to an ionic bond to magnesium. The other chlorine wants to bond once, 1 bond. And then here, magnesium sticking to 2 chlorines. It has 2 ionic bonds. And just a small detail here, this is incorrect. If you draw a Lewis dot structure like that, that's wrong. Why? Because when you draw a line, it means covalent bonding. It means, hey, chlorine and magnesium, you guys are sharing these 2 electrons. No, they're not. Magnesium says, I don't want any electrons. Kick them out. Kick out my valence electrons. I'm a +2 cation. Chlorine says, yes, thank you. I wanted those electrons. We're not sharing. Covalent bonds all about sharing. So do not put lines in your ionic compounds. And then I think I gave away the, oh wait, nice little shortcut. So that's how I did, how I predicted bonds as a student and now as a teacher. And then several years ago, I had some students say, oh, you're talking about honk. What? Honk, H-O-N-C instead of H-O-N-K. Honk the horn. Yeah, but if you remember H-O-N-C and just count the numbers, 1, 2, 3, 4, carbon bonds 4 times, oxygen bonds twice. Ooh, that's cool. So if you don't have a periodic table handy, remember honk. Also remember that H stands for halides as well as hydrogen. So the halides and hydrogens prefer 1 bond. Yeah, we already said that, right? Fluorine, who do I say? Chlorine. We said chlorine was in column 7 and wanted 1 electron. Chlorine wanted 1 bond. And honk is another way to remember that. It's the first letter in honk, so it wants 1 bond. Cool. Nitrogen, 3rd letter, it prefers 3 bonds. Oh, key term here is usually, right? So this molecule happens to be ammonia. Nitrogen's bonding the, and I put a lone pair there, sorry, I have a habit. Nitrogen is bonding the 3 hydrogens. Each hydrogen bonds 1 time. So yeah, nitrogen's getting 3 bonds here. It's bonding normally. But if you had a chance to learn your polyatomic ions, you need to know about the ammonium ion. And in this molecule, nitrogen's attached to 4 hydrogens. It's making 4 bonds. So this is not a hard and fast rule. Yeah, nitrogen prefers 3, usually. Here's an example. Oh, darn it, it's making a 4th bond. So we're going to see some exceptions. Just be aware that they exist. And we'll have other clues as to know, to let us know. Like in this case, hey, how do these 4 hydrogens stick in the nitrogen? Well, it must be 4 bonds of nitrogen. Cool, knock down those 2 guidelines. They're good ones. Ionic or covalent. I kind of already said this, but let's reiterate it, just make sure we got it. Usually, little lawyers talking here. If you have a metal and a non-metal, they tend to make ionic bonds. So I got the periodic table over here on the right. We're going to use that a lot today. And remember, the staircase separates the metals. Metals are on the left side. And up here in the upper right are the non-metals. Where's our exception? Hydrogen. Come here. Up here already. There it is. That's also a non-metal. And I like this periodic table because hydrogen seems to be floating off the table because it's a gas, reminding us it's not a metal. It should be on the other side with the other non-metals. Okay, so if you pair up 1 element from the left with an element on the right, they usually don't share electrons. They don't make covalent bonds. They make ionic bonds. The metals will be cations and positive. And if you forget that, go pick one. Sodium, what do you want to do? I want to lose an electron. If you kick something out that's negative out of your life, you'll feel much more positive. Yeah, same as sodium. Kick out its negative electron. Sodium then becomes a +1 cation, positive. Chlorine, it wants to gain 1 electron. Has 7, wants 8. So pick up an electron. Electrons are negative. So if you get an extra electron, that makes the atom negative, or an anion. Oh yeah, we had the other video, the anion looks like onion, that make you cry, that's got a negative. Cations, meow, are positively positive. Whatever works, right? Whatever helps you remember. Okay, so that's the way you can predict usually. And in this class, it's pretty, I don't intend on giving you a whole bunch of exceptions, but they're out there, right? So usually, most of the time in this class, if you see a chemical formula and there's a metal paired up with a non-metal, use the periodic table to find out if they're metals or non-metals. But if you have one of each, it makes it ionic. And then that's what I remember. Metal with non-metal, it's ionic. But what if you don't have one of each? What if you just have 2 non-metals? Well, then it's not ionic, meaning it's covalent. It's meaning that they're sharing a pair of electrons. Oh, and yes, 2 metals can form a covalent bond. Metals mix with metals to form alloys, and they make some type of weird metallic bond. Anyways, we're not going to see a lot of that. Textbook chemistry will explore that topic in more detail. But anyways, it's following the pattern. If you have 2 metals, they're not ionic bonding. If you have 2 non-metals, not ionic. It's covalent in both cases. Chemistry, why? We have all these rules and guidelines, and we also have exceptions. Okay, so the big exception here of the pattern that usually a metal atom with a non-metal should be ionic, the big exception are those polyatomic ions. Another reason why we need to memorize them. So for example, one of the polyatomics that you need to memorize is dichromate. It's got chromium, so chromium, well, if you like cars and you like the chrome on your car, that's chromium metal. Yeah, so chromium's a metal. And oxygen, where's that? It's on the right over here. It's a non-metal. Okay, so I was expecting a metal and a non-metal to make an ionic bond. Ooh, but this is one of the special ones we had to memorize. A polyatomic. Turns out the atoms of chromium, 2 atoms of chromium, the 7 atoms of oxygen are covalently bond together. Why do we need to know that? Well, later when we talk about salts, maybe containing dichromate, when they dissolve in water, ions separate from ions. But atoms that are covalently bond remain stuck together. In other words, if you put dichromate into water, it stays Cr2O7. The O's and the Crs don't separate and dissolve away from each other. No, they're tightly bound together in covalent bonding. A table salt, NaCl, right? Na is plus, Cl is minus. So crystals of salt, the cations separate from the anions once they dissolve in water. But if you had sodium dichromate, the dichromate ion separates and the 2 sodiums separate. That's as far as it goes. The Cr does not separate from the O's. That's just how covalent bonding is different from ionic bonding. Cool. What's next? Oh, yes. Okay, this is really a minor topic. But, you know, if you take the MCAT or the dental admissions test and they really want to be nitpicky, they might choose this topic. It's like, ooh, how well do you know your general chemistry? Okay, what is this covalent bonding then? Okay, coordinate covalent bonding, sorry. First, the usual case. There's a lawyer speaking again. Usually a covalent bond forms between 2 atoms that are sharing electrons, where each atom is going to provide 1 electron. All right, so I started to put a reaction here to make a molecule of Br2. So where's Br? Periodic table again. Bromine's element 35 on the right. More importantly, it's in column 7. So it has 7 valence electrons. 7. So let's draw the Lewis dot structure. So in a previous video, we talked about how you had spread out those 7 electrons, and the legal places to put them in a Lewis dot structure are on the top, on the right, on the bottom, and on the left. Okay, so I've put an electron in all 4 regions. That was 4 electrons, but there's 7. Now I can pair up. So I'll pair up one here. I'll think about pairing up one here, but a nice pattern is I want to make a bond. So leave a single electron facing the other atom, and it'll help you figure out the Lewis dot structure of the molecule. So I got 6 dots, I needed 7. I'm going to pair up the other ones. I'm going to do a similar trend over here. Bromine gets 7. This bromine on the right gets 7 dots. Now it has 4. I don't want to pair up facing the other atom. So I'll pair up over here. That's ugly. Make it bigger. There we go. 7 dots around bromine. I'm a visual learner, so you don't have to do it this way, but I think about connecting this dot to that dot to make the Br2 molecule. And if you draw the Lewis dot structure of it, this is one way you would draw it. One line represents 2 dots. I should say 2 electrons. Okay, so this is a good Lewis dot structure. What's the point of this? That's the normal way covalent bonds form. One atom will supply 1 electron. The second atom supplies the second electron, and that makes a pair. That makes a covalent bond. Cool, that's the normal way. Each atom supplies 1 electron, and they meet up in the middle. A coordinate covalent bond's different. It's still the sharing of 2 electrons. That's the definition of covalent bonding, sharing 2 electrons. But this time, 2 atoms come together and only 1 atom supplies both electrons. So, got a couple examples here. Let's do water, and let's draw water like this. The Lewis dot structure of water, right? So, hydrogen makes, honk. 1, 2, 3, 4. Oxygen makes 2 bonds, hydrogen 1. So 1 line to H, 1 line to this H, and then 2 lines of O. Good, we're bonding normally. But we need an octet. So oxygen sees 2 lines. 1 line equals 2 dots. Oxygen only sees 4 dots, 4 electrons. It needs to see 8. So this is a fast way of getting to the Lewis dot structure of water. That's correct now. 8 dots, 8 electrons are around oxygen. Boron, we'll discuss this more later in this video. Boron can do an exception to the Octet Rule. Nature actually allows boron to make stable molecules where there are not 8 electrons around boron, but 6. Boron is okay with 8, but it can also do 6. Fluorine, how many electrons does it take? Well, honk, the H says 1 bond. H stands for hydrogen and halides, so the fluorine wants 1 bond. Let's do a Lewis dot structure and make sure that fluorine comes in with 7 electrons, 7 for fluorine. Boron is in column 3, so 3 electrons for boron. So we'll talk about the formal way of doing the Lewis dot structure at the end of this video, but let's do it that way. Here's one way. Fluorine had 7 dots, so I know that's in the corners, but I'm visual. Boron has 3 dots, so I'm facing the odd electron towards the other element. Fluorine, whoops, only give it 4 dots, give it 7. Right, so I know it's kind of messy. There's 7 dots around this F. 7 dots, well, they're going to be 7 dots. I got 1 here, and I'm supposed to spread them out, 4 in each region, and then pair up the ones that are not facing the atom I want to bond to. Same thing on this bottom, fluorine. Take the shortcut, there's pairs away from the boron. And then, let's pause there so you can take a look at that. And then I connect the single dots together. So these two electrons are being shared in a covalent bond. And there's our Lewis dot structure. Right. Just redrawing it. I don't know if that's any more clear, but it's the same molecule. Okay. We got this BF3 molecule and the H2O molecule. Right now, everybody is a regular covalent bond. Actually, you saw that these atoms are each supplying one electron to form the covalent bond. Nothing weird or special here. What is weird is that water will react with boron, mainly because boron is okay with 6 dots, 1, 2, 3, 4, 5, 6, but it can make it can have 8 electrons too. So we can actually make a bond between oxygen and boron. So let's rewrite the water molecule. And I'm about ready to put in the lone pair, but I'm not going to. I'm going to do that in a minute. Boron, I'm going to push one of the fluorines, this fluorine on the left side, I'm going to push it straight up. It still has all 3 of its lone pairs. The other boron, I'm going to kind of swing it down, just make it easier to draw. And also, these bonding electrons are electrons that repel each other. They're kind of going to spread the atoms out so the electrons can repel each other and get farther apart. Okay, so what I did is I rewrote the BF3 molecule this way. Water, or rewrote it same exact way, but instead of the 2 dots belonging to oxygen, oxygen is going to share them with boron and make a 4th bond. And this is the product. So if you're getting confused, let me just simplify it and give you an exam question. So I might say, hey, H2O and BF3 makes this molecule. Label any coordinate covalent bonds. And you'll say, what? Well, these lines are covalent bonds. There's a covalent bond here, here, there, 3 of them, 4, 5, and 6. Where did this bond come from? That came from fluorine with 1 dot, 1 electron, boron with 1 electron. That's the normal way of doing it. That's true of this one and this one. These are normal covalent bonds. What about this bond though? That's where oxygen supplied both electrons. Boron didn't do any work. This is the coordinate covalent bond. If you allow me, just abbreviate it because it won't fit. There we go. This is the bond. That's the special coordinate covalent bond. Because it came from the combination of 1 atom supplying both electrons and the other one didn't supply any. Cool. Let's do another example. Got one right down here. Hey, that's ammonia again. We just talked about that a minute ago. So the Lewis dot structure. Oh, maybe I should have done it the proper way. Let's start all over. Sorry. Nitrogen. How many valence electrons do you have? Periodic table, please. Here's nitrogen, element 7. It's in column 5, so 5 valence electrons. How about hydrogen? It's above column 1. It's not an alkali metal, but it does have 1 and only 1 valence electron. Okay, nitrogen, you had 5, so 1, 2, 3, 4, and I'm going to put the 5th one up here. Hydrogen, you get 1 dot. I'll put it facing nitrogen. There's 3 H's, so the second H I'll put down here and put its 1 dot facing nitrogen. Third hydrogen's over here with the dot facing, and now I just connect them. These are not coordinate covalent bonds, right? Because each atom's supplying 1 electron. H plus, how many electrons does it have? Trick question, right? Hydrogen only had 1 electron, but this cation lost that electron. This is a naked proton. No electrons, no dots. Okay, This doesn't have any electrons at all, none to share. Nitrogen has a lone pair. So it turns out H+, which we saw in a previous video, is what acids supply. Acids produce H+. Molecules that accept an H+ are bases. So this is actually an acid-base reaction. A ammonia molecule, want to grab that H+? And says, sure, I'll loan or let the H+ share my 2 electrons here to make a coordinate covalent bond. Well, the coordinate covalent bond is written down here. Why don't we just speed up the handwriting? So the top hydrogen was attached through a pair of electrons. The other hydrogens, those other hydrogens had to supply one of the 2 bonding electrons. And this is an advanced topic, but if you have a species thing, this is a cation this time, reacting with a molecule, another species, this one has charge, this one doesn't. So the whole left side of the equation has a net +1 charge. You gotta balance your charges. So on the right, there still has to be a plus charge somewhere. Well, do you remember your polyatomic ions? This is the ammonium ion. So the whole thing is positively charged. So you just put a plus element right here. That'll be fine. Cool. So there's a coordinate covalent bond. 2 electrons were lent to the hydrogen to make that bond. I probably spent more time than I needed to because it's such a minor topic. But now you know. Cool. Naming covalent compounds. Okay, take a look at the previous video and refresh your memory on how to name ionic compounds. I got part of the procedure here. Okay, for naming ionic compounds, you're going to actually start out the same way when you name covalent compounds. So that's step 1. Pretend they're ionic for a second. Okay, so what happens if they are ionic? How do you name them? Well, the first element in the compound is probably the cation, and you just go to the periodic table and find out the name of it. Use the same name. Put it in a space, and then go look at the second element. That's, if it was ionic, that would be your anion, your negatively charged thing. Well, go find its element name, but don't use the whole thing. Just use a part or a root of it. Chop off the ending, in other words, and then tack on a new ending, ide. That's how you construct it. Right, so what's the name of NaCl? Well, is that ionic or covalent? Well, our guideline was metals bind with nonmetals to make ionic bonds. Na is on the left side, it's a metal. Cl, it's over here on the right, nonmetal. Yep, we have a metal with a nonmetal. That's ionic bonding. Cool. And so the procedure is find the element name of Na. Well, the periodic table says it's sodium. Good. That's the first half of the name. Put in a space. Go grab the element name of the Cl. So what's the name of Cl? It's chlorine. You don't want the whole chlorine. You just grab the root, which is chlor. I chopped off the ene, and now I add ide. So you guys see that before. Sodium chloride. Done. What's all this mono, tetra, and hepta stuff? Okay, if it was ionic bonding, you don't use di-tri-tetra. You don't use any of the prefixes. You just don't. You don't have to, because you can use the periodic table to predict charge, and charge will help you figure out if there are any subscripts, any 2s or 3s down here in your chemical formula. So you don't need to include di-tri-tetra, whatever, in the name. You can get it from the formula if you know it's ionic. Oh, transition metals. Remember, if you grab the name of a transition metal, the name then, ionic compounds only, ionic only, you need to report the charge of the cation as a Roman numeral. Cool. All right, that's how you actually start to name covalent compounds. Follow the procedure for ionic bonding. And then if it's a covalent compound, meaning 2 nonmetals, usually 2 nonmetals do a covalent bond, name them as if they're ionic, and then now you do add the prefix. The reason for that is when you do covalent bonding, you have opportunities to make a single bond, a double bond, a triple bond. And now two elements can actually make more than one compound. And so each different compound needs a different name. You can create different names if you use ditetra, tetra, those prefixes. Let's see some examples. Oh, wait, what's this italic print here? More exceptions to our rules. Chemistry. All right. Just because it's been done this way, the first element, it never gets mono. Even if there's just one atom present, you don't use the mono prefix, even if it's covalent. Just one of those weird exceptions. All right, examples. Okay, Na2O. So Na, find the first name, it's sodium. That's on the left side. Where's O? That's on the right side. Wait, okay, to make us honest, keep us honest rather, I threw in a metal with a non-metal. This is an ionic compound. Okay, I might do this on the exam too. I might just say, hey, the exam question is name it. I'm not going to say name the ionic or name the covalent compound. No, you'll have to figure it out. We got that guideline, right? A metal with a non-metal. A metal with a non-metal is ionic bonding. The rules for naming ionic is element name of the first, sodium. Element name with the end chopped off, so oxygen, just grab the ox, tack on ide, we're done. Sodium's not a transition metal, yeah, we're done. What about CO2? Well, you probably already know what that's called. We'll just follow the procedure, make sure we get the same name. CO2, so C, it's right here above the staircase, non-metal. Oxygen, also non-metal. Two non-metals make a covalent bond. Okay, the C, the element name is carbon. O is oxygen. So we start out by giving it an ionic name. So I would say C, the element name is carbon. Ox is the, well, it's oxygen for O. But we're going to just grab the ox, add ide. So carbon oxide, if it was ionic, we would be done. But this is a pair of nonmetals. It's a covalent bond. So now we must add the ditride tetra prefixes. Carbon, there's only one. One means mono. Oh, wait, that was our exception. Don't put mono in the front of carbon. Oxygen has two. Di means two. So we put the di prefix in front of oxide. And yeah, CO2 is carbon dioxide. I know, you already knew that. Awesome. What about CO? That exists. In fact, it's poisonous. In fact, there's little detectors, hopefully, in your house to make sure you don't have too much of this or any of this in the house. It has no odor, it's toxic. What's the name of CO? Well, still carbon, the C, still ox, add ide, but now it's covalent compound. There's the ionic name, carbon oxide. Wait, that's not right. This is covalent, two nonmetals, so add the mono and di. There's only one carbon, but don't put mono, one atom for the first element. There's one oxygen, yeah, oxygen is the second one, so you do add the mono. So, and there's different ways of spelling it. You could just have one O here, or you can have a pair of them. Carbon monoxide is the correct name for CO. Yeah, and carbon monoxide is poisonous. It happens if you don't completely burn the natural gas in your water heater or in your oven or any other type of flame in the house. It doesn't get enough oxygen. Normally when you have a fire, it creates carbon dioxide, but without enough oxygen, you make the hazardous one, carbon monoxide. Okay, so there's two compounds that have C and O in it. There's actually more than 3 compounds that have N and O. So that's why you need the ditride tetra to get different names for these compounds of nitrogen and oxygen. So what are their names? Well, there's 2 N's. Well, we should do the procedure, sorry. So there's an N. The name of N is nitrogen. Element 7, go take a look at the periodic table. Oh, we already did that. That's oxygen. chop off the ending, add ide. So this is nitrogen oxide. I don't have enough room. Looking ahead for my next part. Nitrogen oxide. And then this 2 is for the nitrogen. So dinitrogen to tell us, oh, there's 2 nitrogens. And there's only 1 O, so you need the monoxide. And this time I will just have 1 O there. Monoxide. If you put in 2 O's, full credit. That's okay. This only has 1 N, so, but it's the first element, so I don't use mono here, nitrogen. And then it's oxide, 1 O, I use mono again. So this is nitrogen monoxide. Last one, there's 2 N's, so dinitrogen. And there's 4 O's. So you remember that game with 4 cubes, Tetris? So it's tetra. Tetra meaning 4. Go play that video game to remind yourself Tetris. Every object on the Tetris game, they all had 4 cubes attached in different shapes. Anyways, tetra oxide. You can also see tetroxide. I know. Dinitrogen tetroxide, tetraoxide. Your choice, full credit either way. I think that's it for naming. Cool. I think that's the end of this row. Yep. Let's go back up top and over to the right. Oh, on the last thing, the Lewis dot structure, a formal procedure. So we did a couple of Lewis dot structures today, the quick and dirty way, I guess you'd say. But here is a more precise formal procedure. So let's read through it and then we'll do a couple examples. Okay. Formal procedure for doing Lewis dot structure. So follow this procedure if things get weird. It's not easy, just go grab the valence electrons and randomly connect them. You know, put 1 dot facing the other element. Okay, if that doesn't work for you, this method will or should. Get some practice so it does work for you. Okay, step 1, count up all the valence electrons. So go through your chemical formula and just for every atom, find out which column it's in. If it's in column 1, it has 1 electron. If it's in column 2, it has 2, so forth. Count them up. Also look at your chemical formula. Is it an anion? If it is, you add 1 more electron, right? So you're counting up valence electrons. So if the molecule has charge and it's negative, give it another electron for each negative charge, right? So if it's a -2 molecule or ion, -2 anion, you have to give it 2 more electrons than the number of valence electrons you already gave it. And then do the opposite if you have a cation. You counted up all the valence electrons, but if it has a +2 charge, subtract 2 of those electrons away. To become positive, it had to give up some electrons. And if it's a +1, then it gave up 1 electron. If it's +3, take away 3 more electrons. That sort of thing. Cool, so now you have the pool of electrons. You have the total number. What do you do with them? Start linking the atoms together in covalent bonds. At a minimum, give, and that's how you start, at the minimum. Choose 1 atom to be in the middle, the central atom. I'll give you some guidelines on how to choose. But pick one of those atoms to be in the middle, and then connect all the other atoms through 1 covalent bond. And remember, the 1 bond is going to use up 2 of your valence electrons. How do you find the middle atom or the central atom? I got 3 guidelines here, and I'm sorry I don't have something more clear. Just as you get more practice, you'll get a better feel for it. And if I give you a test problem and it's not obvious, or I think that these 3 guidelines won't give you a good answer, I'll tell you. I'll say, okay, in this problem, this atom is a central atom. Please draw the Lewis dot structure. Okay, what are the guidelines? Try going with the atom listed first. Doesn't always work. Use HONC, or predict the number of bonds that the atom can make. And the one in the middle is probably going to need a lot of bonds to connect all the rest of the atoms. So the central atom is usually the atom that can make the greatest number of bonds. Or it might be the one that's listed first. The other idea I see a lot is that you pick the atom that's the least electronegative. That's a topic of our next video. For now, just realize that the electronegativity is a property that is greatest in fluorine. And so fluorine has the greatest electronegativity. It's over here at element 9. And the pattern or the trend is that elements close to fluorine are also electronegative. But this electronegativity property drops off the farther away you are from fluorine. So a third way to predict who's in the middle, who's the central atom, is the atom farthest from fluorine located on the periodic table. Okay, that might have been one of our hardest steps. Who's the central atom? Well, try the first element listed. But that doesn't work for H2O. Why not? Honk. Hydrogen only makes one bond. That's not going to be in the middle with only one bond. Anyway, so then go with the atom that makes the greatest number of bonds. There you go. Anyways, moving on. Let's see some examples in a second. Step 3. Let's review real quick because I kind of lost track. You count up all your valence electrons. You made some modifications. If it's an anion, you gave it more. If it was a cation, you took away some electrons. You pick the middle atom, and you connect all the atoms to it using a bond and used up some of your electrons. Okay, you still have electrons left over, hopefully. Add them to the, not the central atom, add them to the outer atoms so that they obey the octet rule. Make sure that each atom around the molecule can see 8 electrons, 8 dots. The octet rule is the way we can predict whether the molecule will be stable and can exist or not. And so a good rule of thumb is if you can get 8 dots around every atom in your molecule, that's a good indicator that that molecule probably exists in the real world, or it could be made in the lab. What if you didn't run out of electrons, you still have extras? Well, just dump them in pairs on the central atom. Well, what if you didn't have enough to get octets for everybody? Well, that's step 5. You don't have enough. Well, go look at your lone pairs that you already gave to the outer atoms and borrow those and start doubling up or tripling up bonds. That should help give every atom, every atom an octet. Okay, let's give it a try. I got several molecules down here. Let's try all those dot structures for. Before we do that, quick little review of the octet rule. And then again, this is nice, not nice. This is a common pattern we see in chemistry. Hey, there's this cool rule. 8 dots around every atom makes a stable molecule. At least that's a prediction. Cool. Oh yeah, we have exceptions. And not so cool. What are those exceptions? Well, we already mentioned one. Hydrogen, it just needs 2 electrons. You could call it the duet rule instead of the octet rule. Boron, we mentioned earlier in this video, is okay with 6 or 8 dots. So is aluminum. So how are you going to remember boron and aluminum? Well, based on their position helps. They're right here at the edge of the p block. Remember when we were doing S, P, and D, electron configuration? So boron and aluminum are 2 elements that nature says, you're okay with 6 dots. Your compounds can exist. But you know what? Try making 8. So they can also have 8 dots or 6. What else? Last one, I believe. For elements that are in the 3rd row or lower, they like doing 8 dots. They obey the octet rule, but sometimes they can do 10 dots instead of 8 or 12 dots. So here's the 3rd row. So elements that are in this row or lower, try and give them 8 dots. But if you have extra electrons left over, you can dump them on them and they can deal with 10 dots, 10 electrons, or 12. It's okay to give them extra. And the reason for that is that once you get in the 3rd row, you're in the 3rd shell, and the 3rd shell has the d orbitals, right? There's a 3s, then the 3p, the 4s, and then you get into the transition metals, start filling the 3d. So once you're in the 3rd shell, an atom is putting electrons in 3rd shell, there are d orbitals the atom can use to make extra bonds or to dump in extra electrons. So that's the reason why third row or greater can have 8, 10, or 12 dots. Fun stuff, chemistry. All right, we're going to end the video here with some examples. Okay, let's play the game. What's the game? Here are the rules. Step 1, please. There is step 1, count valence electrons, adjust for anions and cations. Step 2, link the atoms to a central atom. The linkage is through a bond, a covalent bond that uses up 2 electrons per bond. Trick is going to be picking the central atom. See if it's the first element listed in the formula, or the one with the greatest number of bonds, or the one farthest from fluorine. After that, fill the outer electrons with octets. If you still have electrons, dump them on the central atom. Then check every atom, make sure they see 8 dots. If they don't, then go borrow lone pairs and start making double or triple bonds. That's the game. Let's give it a go. Let's make water. I know we already did it. Let's just do the formal process. Okay, step 1, count valence electrons. Use your handy dandy periodic table. Hydrogen is in column 1, so it has 1 dot. Oxygen is in table 6, 6 dots. So I'm counting them on step 1. Hydrogen, there's 2 H's. Each one has 1 electron. There's 1 oxygen. That comes in with 6. That's a time, sorry. 2 times 1 is 2, plus 6 is 8. 8 total electrons. That's step 1. I counted them all up, and it's not a cation, it's not an anion, no adjustment. Step 2, attach the atoms to a central atom. Well, is H the central atom? No, because of honk. 1, 2, 3, 4. Hydrogen makes only 1 bond usually. Oxygen makes 2. Hydrogen's not going to be in the middle. If you put a hydrogen in the middle, that gives hydrogen 2 bonds. You can't do that. That's a bad Lewis dot structure. Okay, so use oxygen because it makes more bonds than hydrogen. It's the atom making the greatest number of bonds. So oxygen, you go in the middle, put the hydrogens on either side. And remember earlier, I decided to put one down here. We'll talk about why this is actually a better choice than this one. We'll talk about that in our next video. But for today, Lewis dot structures, or anytime I ask for Lewis dot structure, if that's all I'm asking for, you can put the H's like this arrangement or like this or some other combination, just as long as the oxygen's in the middle. Oh, step 2 says also link them up. I just used 2 electrons there. That's a 2, minus 2 gives me 6. I used another bond to connect the other H. That's another 2 electrons. I'm down to 4. Step 3, give electrons to the outer atoms until they have an octet. Well, hydrogen just satisfied the duet rule. It's good with these 2 dots. Step 4, dump the rest 4 electrons on the central atom in pairs. And I'm done. Ooh, but check and make sure everybody's got an octet. Hydrogen, how you feel? Good. It's seeing 2 dots. So is this hydrogen. The oxygen, well, it has access to all of these. It has the 2 pairs above and below, and it has the 2 bonds left and right. 1 line equals 2 dots, so there's 2, 4, 6. 1 line equals 2 dots, and 8. Yep, octet satisfied. That's a good Lewis dot structure for water. And this one's also a good one, actually a better one, for a reason we'll see in the next video. Sulfur and chlorine. Let's name it real quick. Why not? Are these metals or non-metals? Let's go to the periodic table. Sulfur and chlorine. Sulfur and chlorine right together in the upper right. They're both non-metals. This is a covalent compound. Sulfur is in column 6. Chlorine is in column 7. 6 and 7. And they're non-metals. So the name, S was sulfur. chlorine becomes chloride. So this is sulfur chloride. Ooh, but it's covalent, so I need to add the ditritetra. This compound is sulfur, no mono, on the first element, dichloride. Cool. So now let's draw the Lewis dot structure of sulfur dichloride. Count up the valence electrons. Sulfur had 6, chlorine had 7, and there's 2 of them. So 6 plus, well, 7 times 2 is 14. 6 plus 14 is 20. 20 electrons total. And it's not a cation or anion, no adjustment. Okay, central atom. Try the first element listed, sulfur, and it turns out that works. How about the atom that makes the greatest number of bonds? Well, what would we predict for sulfur? Sulfur is in column 6. It wants 2 more to be like argon, the noble gas. Yeah, 2 more to get to 8. So sulfur is going to make 2 bonds. Chlorine just wants 1 bond. It's a halide, honk. H stands for halide. It only wants 1 bond. So the sulfur atom makes more bonds than the chlorine atom. So that's another reason why it should be the central atom. Okay, and then you can put the chlorines left, right, like we did for water, or you can put 1 left, right, sorry, 1 to the left, 1 down, or any other combination. All right, I'll do a different combination. I'll connect the chlorines like that, whatever. Sulfur still is the central atom. And, ooh, I used up 1 line, 2 lines, 1 line equals 2 dots. I've used up 4 electrons. Now there's 16 left. Okay, next step, fill the outer electrons so they have octet. So right now the line means chlorine sees 2 dots. An octet is 8. So I need 6 more to give this chlorine 8. So I used up 6. So now I'm down to 10. Let's fill up this chlorine, 2, 4, 6. This chlorine now sees an octet. Used up 6. That leaves 4. Okay, then dump them on the central atom in pairs. So you get 4 dots here and there. We used them all up. Yay! Check and make sure it's an octet for everybody. Okay, sulfur, how you feel? Good. I see 8 dots. 2 lone pairs, 2 bonds. 1 line equals 2 dots. There's 8 dots around sulfur. Chlorine, how you feeling? Nice. Good. You have 1 line and 3 lone pairs. 1 line's 2 dots. Yeah, there's 8 dots there. And so is the other chlorine. This is a good Lewis dot structure. Sorry, and I got all my circles around it. So let's redraw it real quick. There we go. Full credit for a Lewis dot structure like that. All right, let's squeeze the hydronium ion. That's one of our polyatomic ions, right? Draw that over here. Okay, hydrogen is in column 1. It has 1 dot for every hydrogen, 1 electron. There's 3 of them. Oxygen is in column 6A. Double check. Yep, still in 6. It's always going to be a 6. Oxygen has 6 valence electrons. And we're adding up all the valence electrons. So there we go. So right now there's 9 valence electrons, but it's a cation. So how did it become positive? It kicked out an electron. So it has 1 less electron, giving it a total of 8 valence electrons. And opposites is opposites. Doesn't that suck? A plus charge means you subtract 1. There's so many opposites in chemistry. But reason it out. That's how I do it. Hydrogen came with 1 electron each, so there's 3. Oxygen came in with 6 electrons. How does this become positive? You had to take away an electron. So there was 9 valence electrons, but make it positive, we're left with 8. 9 minus 1 is 8. That was step 1. We're step 2. Connect the atoms to a central atom. Well, oxygen makes more bonds than hydrogen, so put oxygen in the middle, hydrogen's around it, and link them. 2 electrons, 4 electrons, 6 electrons. We have 2 electrons left. Well, fill the outer atoms with an octet. Not for hydrogen, it's done with the duet. Okay, and these last 2 electrons, you dump them on oxygen as a lone pair. We hope everybody's got an octet, and yes, oxygen has 3 lines. 1 line equals 2 dots, so 2, 4, 6, plus that pair is 8. This is a stable molecule, and we know it as the hydronium ion. So maybe put a plus charge over there to remind us this is hydronium. Sometimes you'll see a big bracket around it. You can do that too, whatever you care. I don't. Just make sure the plus charge is there, because that's what it is. It's hydronium with a positive charge. What's the name of NO3 minus? Another polyatomic. That's nitrate. So you got to know those for our next exam. I know. Well, chemistry, we keep using these, and yeah, so it's handy to have them memorized. All right, so let's draw a little stat structure. What's nitrogen's valence number? Well, N is in column 5A. Yep. So here, N's in column 5A. Nitrate has 3 O's, so it's oxygen's 6 valence electrons. Nitrate, NO3 minus. So nitrogen had 5 valence electrons. Oxygen comes in with 6, and there's 3 of them. Ooh, and let's make the adjustment. How did this become negative? Somebody gave it an extra electron, and that's what we're counting down here. So give it another electron. Opposite is opposite. So if it's a negative charge, you add in an electron. That's what we do. And then you don't need a calculator for this. 3 times 6, you should know it's 18. I know we're in college, we can do this. Sorry, a little stickler. If you really need a calculator, there's one available on Canvas. When you're taking the quiz, the calculator will be available there. So you can check your math, I know. When you're in the exam mode, anxiety's high, kind of helps to have the calculator just to double check the math. 5 plus 18 is 23, and 1 is 24. Double check my math on the calculator if you wish. It should be 24. All right, that's the total number of valence electrons. That was step 1. Step 2, attach the atoms to a central atom. Well, you could go with the first atom listed, nitrogen. That works. Or you can remember hunk. That's over here in the upper left corner. Nitrogen makes 3 bonds. It's the 3rd letter in hunk. Oxygen's the 2nd letter. So nitrogen makes more bonds, makes it a better candidate for being the central atom. So put nitrogen in the middle, link the 3 O's to it. Electrons, 6 electrons. And that should be 18. Step 2 is done. Link the central atom to all the other atoms. Step 3, give an octet to the outer atom. So oxygen, you need 2, 4, 6 more. Now this O has an octet, and I used up 6. Do the top one. It's got 1 line, 2 dots. So give it 6 more for an octet. 6 electrons remain. Ooh, that's just enough for this oxygen. I've used them all up. Am I done? Do I have to get full credit for this? No, check the Octet Rule. Ugh. Oxygens all have 8, but nitrogen doesn't. Nitrogen's only looking at 3 bonds or 6 electrons, right? 1 line is 2 dots. Well, I don't have any more electrons. It could really use a lone pair. Sorry, there are no more electrons. No lone pair for you. So now what you have to do is borrow a lone pair from one of the outer atoms. So, and you get to pick. If you've heard of resonance structures, that's going to come into play as to which oxygen you're picking. We're not going to do that today. Just give me one Lewis dot structure for now. So I'm going to pick this oxygen. So where's my eraser? So I say, hey, oxygen, will you help nitrogen out? It doesn't have an octet. You didn't see oxygen being too happy about this. Sorry. It's all in the good in the whole molecule. I'm going to take those 2 electrons, and you still get access to them, but now you're going to share them with nitrogen. Thank you for being a good neighbor. Okay, so you took away that pair of electrons and put it in between the N and O, so they're being shared. That's what the line means. Covalent bond. We now create a double bond between this left oxygen and the nitrogen. And nitrogen's now happy. It's seeing 4 lines, 4 bonds. So there's 2 electrons, another 2 is 4, 6, and 8. There we go. And then I like putting the negative charge on here because this is nitrate. So you put the minus sign just out and open like that. There are more formal charges here if you've heard about them. The other way you could do this is, I'm going to put that into a bracket and put the minus charge out here. That's another way to display that this is nitrate. Okay, last one, C2H4O. C2H4O. Okay, save the worst for last. There are a lot of atoms here. I'll just jump in, follow the procedure, see where it takes us. Step 1, count the valence electrons. How many valence electrons does carbon have? Well, it's in column 4A. You can also remember HONC, H-O-N-C. C is the 4th letter, 4 bonds, so it had 4 electrons to gain or lose. That works too. Carbon, you have 4 electrons. There was a hydrogen, you have 1 electron, 1 valence. Oxygen, you have 6. Carbon, you're in 4A, you have 4 valence electrons, and there's 2 of them? There are. Okay, so counting valence electrons, carbon comes in with 4. There's 2 carbon atoms. Hydrogen comes in with 1 valence, but there's 4 hydrogens, so multiply by 4. Oxygen, you came in with 6. 4 times 2 is 8, plus 4 plus 6. 6 and 4 is 10. That gives us 18. Step 1 is done. There are 18 electrons. It's not a cation, not an anion, no adjustment necessary. Who's my central atom? I'll go with the first element listed, carbon. Or go with the one that makes the greatest number of bonds. H-O-N-C, 1, 2, 3, 4. Carbon wins. It makes 4 bonds, usually. But which carbon? Okay, so when you have lots of atoms, you could put the carbon, I would pick to put the carbon in the middle. And then you could just put the, oh, maybe I'm making an assumption here. Start over. One idea, put the carbon in the middle. There's 2 of them, so maybe put 2 in a row. Then there's 4 H's. Any red flags going off yet? And then put the O. How do you like that? Hate it. Here's one reason. Hydrogen can only make 1 bond. You just gave it 2. And lots of times, this is horrible. That's a bad molecule. That does not exist. You do not get a chain of atoms like that because hydrogen can't make more than 1 bond. Okay, so if how many bonds does hydrogen make? 1. So if you decide to put a hydrogen here, you can't extend the chain anymore. That's okay, because how many bonds does carbon make? It makes 4. So why don't you go ahead and give 4 bonds to each of those C's? I'm doing a little shortcut here. Maybe I shouldn't. But keep that in mind. 4 bonds of carbon usually. All right, let me do the procedure properly. We first counted the valence electrons. Now we're connecting the atoms to the central atom. I picked C. Okay, there's 4 H's. Can I put all 4 H's on one of these carbons? How many bonds does this carbon make? 5. Is it in the 3rd row? No, it's in the 2nd row. It can't make more, it can't have more than 8 dots. Okay, told you this one's a tough one. Okay, so keep HONC in mind. It's going to help you do better Lewis dot structures. So 4 bonds max of this carbon. So yeah, maybe I want to put an H here and H there, trying to connect all 4 of these H's to the central one. But as soon as I get 4 lines of this carbon, I'm done. Carbon maxes out at 4 bonds. So now put the fourth hydrogen maybe on this one, and then put the O. This actually is going to work. That's crazy. That was step one. That was step two. Sorry. Step one is counting up 18. Step two, link everybody together to the central atom. Now, some of you might be saying, well, which is essential, the left carbon or the right one? The answer is yes. They're both in the middle. That's what's going to happen when your molecules get too big. You're not going to have one and only one middle carbon. I'm sorry, middle atom, because you'll have this situation that's impossible. You can't connect every atom to one in the middle. So this is how you get around it. Count up the number of electrons they used up. So there's one bond, which is 2 dots. So there's 2, 4, 6, 8, 10, 12 electrons I've already used up. That leaves 6. Okay, go to the outer atoms and give them octets. Hydrogen's done with its duets. Okay, so 2, 4, 6. I just gave oxygen an octet. I used up all the electrons. We're all done. Am I done? No, check the octet rule. Oxygen's fine. This right carbon is fine. It's got 4 lines to it, but the first carbon's not happy. 3 lines, 6 electrons. But there's no more electrons, can't give a lone pair. So you have to borrow from another lone pair. So sorry, carbon. Sorry, that's oxygen. Sorry, oxygen. I need you to be a good neighbor again. So can I borrow those? You can still have access to them. I'm gonna put them right here, but you need to share them with the carbon. And there you go. That's actually one molecule you can make here. So if you're fine with that, you can stop the video, we're done. But here's another choice. If you had worked ahead, I didn't really pause the video to give you that chance, but if you did, you might have said, okay, I'll put 2 carbons kind of in the middle. I'll connect an oxygen. And then I'll put 2 hydrogens here. Ooh, but this carbon maxed out with 4 bonds, so I have to put the other hydrogens here. And then 2, 4, 6, 8, 10, 12. We started with 18, let's take away 12, we got 6 again. Dump those extra electrons on the outer atom to give it an octet. We're done. And now we have a problem. This carbon's not happy, no octet. But I can't borrow this lone pair and put it here because that's 5 bonds to this carbon. I can't put it here because that's still 5 bonds to this carbon. So I did this on purpose to show you that, hey, I'm following the procedure right, but there's so many atoms, I came up with a bad pattern of connection. The way I attach these H's in that O, it's impossible to give this carbon octet and have everybody else satisfy Octet Rule. So this is not going to work. One way to fix it is to draw this one, move the oxygen to the other side. I don't know if you would have thought of that if the very first time doing that you set things up this way. But one idea is instead of having the hydrogen connect to the 2 hydrogens to this carbon, why don't you put 3 hydrogens on the other? I had 18 electrons. I got 2, 4, 6, 8, 10, 12. Good. 6 again. Dump those 6 on oxygen. This carbon's not an octet. And ooh, now I can borrow this and put the double bond here. And now this oxygen sees 8 dots. This carbon sees 8 dots. We're happy again. So there's actually 2 molecules with the formula C2H4O. These 2 molecules. Wait. You have a C with double bond H, C with double bond H, and a CH3 and a CH3. I just drew the same molecule twice. These 2, if you take the computer screen and flip it upside down, this drawing will be this drawing. They are the same. But you know what? There still are 2 molecules with that formula. So I'm going to end the video with that. So if you're happy, we got a Lewis-Dot structure, run off and go do something else or take a break. But here's the last method. C's in the middle. O next. Think about putting my H's here. Well, why can't I put it there? You can. And then I don't want to put, do I? No. I don't want to put the other H here because that'll be 4 bonds here. So if I decide to put the 4th hydrogen here, this is going to be missing the octet, and the lone pair is going to be too far away to help. So instead, I'll put the, wait. I have 4 H's. I already used up all my H's. Sorry. Dennis can't count. I'm done connecting atoms. 2 carbons, 4 H's, 1 O. I put one of the H's on the oxygen, which is legal. You can do that. Water has 2 H's. Why can't this O have an H? You can. How many electrons did I use up out of the original 18 valence electrons? 2, 4, 6, 8, 10, 12. Yeah, you know that pattern. 6 left over. Give the outer electrons, sorry, outer atoms. So hydrogen is a duet, so give the oxygen its octet, but that only took 4. So then we got 2 left over, and you're supposed to put them on the central atom. Well, which one's essential? This one kind of feels more central than that one. So maybe I'll dump it here. So this carbon's happy with an octet, but that one's not. So maybe I'll put them over here. Oh wait, but then this one's not happy. Whether you put the lone pair here or there, make them share. There's a double bond here instead. There we go. And now this molecule with a carbon-carbon double bond is different from this carbon-oxygen double bond. Now we have our 2 molecules. There's 2 molecules represented by 1 chemical formula. The word for that is isomers. These are isomers of each other. Different molecules, same formula. That's a little preview and a much later concept. That's plenty for now. Take a break. Thank you, and I'll see you in the next video.